Hey guys, it's your host Subhra. Welcome to your favorite channel, Subhra the Geek. So today we will be talking about inferential treatment using linear models. Today we'll be learning about how to implement least squares or F-statistics or T-statistic inside your model and how to find the value. Guys, these are the series which I, along with my very good friend Debayan, have planned for you guys, which cater to the exact needs of the industry. And what industry to be precise is the industry which, according to Harvard Business School, is the sexiest job of 21st century. That's none other than data science industry. So guys, if you face any problem during the course of your journey, please do comment, or you can follow us on our Discord link that is given below. That's an exclusive Discord server which I have prepared for you guys, where I and Debayan will always be there to help you guys out throughout your journey. Guys, please support us by subscribing to my channel and sharing the videos and giving a thumbs up. Next will be Debayan, starting with inferential treatment using linear models. Let's start, shall we? So Debayan, as we talked in our last video, you will be showing today about F-statistic, T-statistic, and how to calculate them in different programming languages. So what are your thoughts and how would you like to begin?
Okay, we're gonna start off with parsimony, and what do we mean by simplest model possible? So I believe that's where we left off in the previous video. So we're gonna talk about what do we mean by simpler model or simplest models. That's parsimonious model, and from there we're gonna go into understanding how do we do that, as well as perform inference using the F statistic and the T test. So primarily, it's not about calculating those; it's more about understanding and explaining those terms or the implications of those terms as per your model to the layman, right? We want to make it as simple as possible. We want to understand what it means, and we want to convert them into insight. So that's what we are going to do. And to end the video, we're going to talk about stepwise regression. It's like an algorithmic way of finding out a simpler model. So that's one of the interesting aspects of how you can approach. Like if you do not know what to do, then start with stepwise regression, so we can see how we can create a simpler parsimonious model. So that's what we have in store for you today.
So guys, Debayan gave us a brief of what he is gonna explain today. So let's now jump onto Debayan's tab and understand each and everything minutely and in great details.
So consider two variables, right? A and B. So if two predictor variables, A and B, right, they are in a model. You have a model, and they are correlated with each other. That means you have seen that the correlation value of A and B, it's some value. It's not equal to zero, right? So and they are pretty high, right? So the absolute value, you'd say, is pretty high, right? So you'd call them correlated, and in a model, what we call them is collinear, right? Colinearity. I have the spellings correct. Colinearity, right? So they are what you'd call collinearity. In a model, if you have collinear predictor variables, it complicates your model's performance. It complicates the interpretation of your model, and it definitely exaggerates the performance of your model, right? And this scenario is called multicollinearity. Just to explain, just to repeat what I just said, right? So if you have a model f, right, and in f you have many variables x1, x2, x3, and so on and so forth, and they provide an outcome y cap. It's a prediction, right? So if xi, so if correlation of xi and xj, which is where xi and xj belongs to this set of variables, whatever your variables are in your model, right? If it's pretty high, then those variables are collinear. right? And the scenario is called colinearity or multi-colinearity if you have more than one pair of variables. This is not desirable. Not desirable. You do not want to have a model where multiple variables are actually correlated with each other, right? What you want is x is correlated with y. That's what you want because you want to use x to predict y, right? So they should be associated or related with each other in some manner, in some way, right? You do not want x1 is correlated with x2 or x3 is correlated with x5. I don't know, some pair. You do not want that to happen. This thing is not what you want. This is, where's the green? Okay, that's a green. That's a green, right? This thing, this is what you want. This is what you want. This thing, the second one, you do not want that, right? So keeping this in mind, you want to have a model which is small enough to have a very low number of input variables or predictor variables, but a very good performance. You want to keep the model as simple and compact as possible while producing good results. That's what you want. And that one of the simpler ways to basically check collinearity between models is just check iteratively is okay, is x1, x2 correlated? How correlated are they? Is it more than more than 60%, 75%? Right? I work with 75%. If it's more than 75%, I drop it. I drop one of the variables because you can use one to technically derive the other because it's so highly correlated, and that's how you can remove uh, these models, right? So parsimony is the term in which is a state where a model has the required number of predictor variables and no less. You cannot have any decrease in the number of variables that the model has. So you want a compact model with the least amount of variables with the maximum predictive power. That's what is called parsimony. You want to have that kind of model, right? No less with maximum predictive power. And that depends on how do you measure that, what kind of metrics you're using there. Do you use some kind of classification metric, or you use regression metric like some kind of MSE error, standard mean absolute error, mean root square error, like whatever metrics you're using for regression classification. Maybe you're using the F1 score or F2 score, or you're using classification accuracy, precision, recall, whatever value is, it should have the maximum predictive power. So small model, maximum power. That's what you want. You wanna balance those two, right? So what are some of the criterions that you have in a parsimony state, right? So to achieve parsimony, you want to avoid collinear variables in your model. You want to check for that. You want to check between correlation between the predictor variables and remove variables which are like correlate with each other or they're collinear to each other, right? You want to avoid that. They bring nothing new to the table. If I do the same work as another, let's say I'm a company, right? I have two employees, A and B, and can do like 75% of the work which B can do, but B can do more than what B can do, some extra 15% or something. Why will I keep A in the list? Why A doesn't bring on anything? Maybe you need more workers, but you can get the sense, right? You do not need someone with similar skills. You need someone with complementary skills. You need something different. They need to bring something new to the table. Only then they will provide unique value in their proposition. That's called the value proposition, right? So every variable must be unique in what they contribute to influencing the model, right? They must be correlated with the target variable and not with each other. Every variable must be unique in that case. So they must be non-collinear, right? So you want the simplest model with highest predictive power. Highest predictive power, when I say predictive power, depends on what metrics you're using. For classification, you can use any one of the classification metrics: accuracy, recall, precision, F1 score, F2 score, whatever you're using. And for regression, you can use any one of the standard error metrics, right? And you also want to make sure that you are using control variables or controls, right? So what is a control? So if you do statistics 101, a control is a variable where the null hypothesis, like, it's a null hypothesis. Control is a null hypothesis in physical reality. So if you're testing for something, you want to keep a variable which is there, and then create another model where the variable is not there, and see whether including that model actually makes sense. Does it actually create an impact, and is it for the negative, is it for positive, what is it, right? So that's your control. You want to keep in controls, right? In essence, all of this can be reduced to one thing: Occam's razor. Have you heard of these terms, guys? Occam's razor, right? What does Occam's razor say? It says that among the competing hypotheses that you might have in your alternative hypothesis, right? So you have null hypothesis, and you can have, like, like hundreds of alternative hypotheses to your ideas. And so among the competing hypotheses or alternative hypotheses, you want to go with the one with the fewest assumptions or fewest possible, like, dependencies, right? Among multiple competing alternative hypotheses, choose the one which makes or uses less assumptions to produce the same result or variables, right? So choose the one with the simplest one. Choose the one with the least amount of assumptions or input predictor variables, which also produces the same result, keeping that in mind, right? So that's what's called Occam razor. If you have a complicated scenario of choosing a model, choose the one with the simplest one. That's what it is at the end of the day. Now let's move on to the main part of the video, right? So this is continuing from where we left before. Quick summary: where did we leave? So we started with a model, right? Y is equal to m1 x1 plus m2 x2 plus dot, dot, dot. M1 x1 plus m2 x2 plus dot 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 c, right? So this is a model, right? So your null hypothesis is, if you're building a model and you want to see whether this model actually makes sense in terms of inference or predictions, right? So what you want to have, your null model, your null hypothesis is m1 is equal to m2 is equal to m3, all of them is equal to 0. What that does mean is that there is no influence of the individual predictor variables on the target variable. That's what you're saying with the null hypothesis. The alternative hypothesis is therefore essentially the complement of that, which is at least one, coefficient or one mi is not equal to 0. It can be more than 0, it can be less than 0, but it doesn't matter. What matters is it's not 0. That's not the null hypothesis, right? So one of the things that we do, right? One of the things that we do in Python and then in R, that you create OLS models, right? Ordinary least squares equation. That's what linear models are, right? So in Python, there is a module called stats model dot OLS, and then R there is also the LM model or GLM model. You might have heard of these functions if you use those, at least those two languages. And what you do at the end of it, like this a stats model, you do basically do model dot fit, right? And then you do a summary. You do a t-test. There's lots of function in there. For R, what you do is that after you have the model, you just call the summary function on it. There's a global function called summary, and you call it on it, right? Both of this will return you some text. It will return you some value. That those output is what you're going to use to do inferential statistics. You use it to understand whether my null hypothesis works or not, whether my model is actually good or not, right? And this is one of the statements that you will see. This is the statement that you will see near the end of the results from both these two, right, or something similar. You're gonna see something like this. You're gonna see F statistic. So this is the statement, exactly the statement that will happen. It will have some value like F statistic is equal to 19.29.74 on 4 and 429 df. Some statement will be like this, and then it will say p value less than 2.2 e minus 16, right? You will receive some value like this. Let me highlight like this, right? You will see some statements like this. How do you interpret this statement? This is important. That's why I'm showing you guys this. So what it means that the number of predictors in that model is 4. That 4, right? Number of observations in that model or used to train that model is 434. How did that get value? Right, so it because of degrees of freedom, right? So degrees of freedom or df is n minus k minus 1. N is 434. 4 is the number of predictors. 1 minus 1 because intercept. That's also there. So how much value did you get? 429, which is exactly this, right? You'll also get a p-value, right? You will have a p-value. Now this p-value, if p-value is much less than your alpha, alpha is your significance level, right? So how much uncertainty, how much evidence are you how much evidence in contrast to what you expect is are you gonna see before you say that okay, it's too much, I need to change my null hypothesis, I need to reject the null hypothesis. How weird it has to be, how abnormal it has to be before you say okay, I'm gonna caving. I'm gonna say that okay, it's too much. The evidence is overwhelming, and I have to reject the null hypothesis. How much do you want to see that? It's a percentage. It's a probability value, so it has to be a percentage. General values are 1%, 5%, and 10%, right? So over here it's zero. It's 2.2 e to the power minus 6. That 10 to the power minus 6. That's way low. That's less than 1%, right? So you're going to say that okay, the model is significant, p value much less than what your alpha value is, it's significant. That means there is actually something going on, right? So the model in this case, in our example, is actually significant. So whatever variables that I actually had, it's actually significant. That means it actually can produce influential results, it can actually do good predictions, right? The F test has a significant value. That's what given by the p-value, right? So the F test yields a significant result, right? What does that mean? It doesn't mean that the model fits the data well. That's not what is claimed here. What it means is that at least one coefficient of regression or coefficient of the predictor variables is not zero. Going back to the hypothesis, this is what we have evidence for. The p value is much less than your alpha value, which is 1%. So you say that your F statistic value is significant, and that implies that we have to reject the null hypothesis, right? And we have to say that okay, at least one of the slopes, one of the coefficient of regressions, it's not zero, it has to be there. If the F test didn't yield a significant result, that means the p is much more than whatever the alpha value is, which is in this case it's not. But if it was, then it doesn't mean that the variables included in the model are good predictors of y. It just means that the particular combination of these variables is not a good predictor of y. Please understand that carefully, right? So if p is more than equal to alpha, right, that means model is not significant, right? What does that imply on the F statistic? It means that the specific combination of variables used or variables used is not a good combination. It's not a good combination, and it does not yield a great model. That's what it implies. That's what it means if it's not significant, right? Okay. Now let's look into the t-test. Let's look into see how we get the p-value for the t-test for very specific variables, right? If you remember, t-test looks for influence or individual variables and see how they influence the the target variable. So we're going to look into that. So how do we now? Let's look into the t-test, right? So let's say you have this model. Bring this model again back over here. Let's see. You want to test for how much influence that x1 has on y, right? You want to see how significant that is, right? So what you do is that you use a t statistic. So what's your t statistic or t metric, whatever your t metric is t is equal to, in this case for x1, right, is equal to your point estimate, which is for m1, right, minus the null value, which is 0, because the null hypothesis is that all of them are 0, right, 0, divided by standard error. So what's standard error? Standard deviation divided by number of variables, number of observations you have in a data set. That's standard error, right? So m1 minus 0 divided by standard error, right? And your df or degrees of freedom is obviously equal to n minus k minus 1, where n is the number of observations that you have here, k is the number of predicted variables you're using in your model, and minus 1 because there is one intercept value over it that you need to count for, right? So when you have this, you can create a t statistic. So this is your t statistic that you got. You're going to put this into a function called pt, or probability cumulative density function for t, for students t distribution. That's what it means. And you have that under scipy.stats for Python. So under Python you will get it under scipy or scipy how much but stats, and in R you directly get it as pt, right? So pt, you just put in your x value over here, you put in your degrees of freedom, whatever the value is, right? And you say lower tail is equal to false. And then you multiply the whole thing with 2, because there are two tails, right? So you have to, like, if you think of a distribution like this, there are two tails over here, so you multiply that with 2, and then that you basically add this, so you get the if you use pt, you get this one, you get this one as well, you plus them, that's basically the same thing, so that's multiplied by 2, and you will get some answer, you'll get some answer, right? That answer is your p value. If your p value now is less than your significant value, then what you say is that you reject the null hypothesis. You reject the null hypothesis, which is the coefficient for x1 is not 0. That's what you reject, and that means you say that it is statistically significant to say that x1 has some influence on the target variable y, given that I know that m1 cannot be 0. That means there is some variable, and it's statistically significant. If you do a lot of tests, then you will find out that x1 actually has some significant influence on y. That's what you find out using the t-test over here, right? There's also another interesting thing that you get when you use t-test to do this. What you get is a confidence interval, right? It's called confidence interval. And what does confidence intervals mean? So it's like this, right? So your M1, because you did with M1, right? Your M1 plus minus your T value, which is X1, multiplied by your standard error, whatever that value is. So this boils down to M1 minus T statistic into standard error, M1 plus dot SE. You get a range. Both of them are inclusive, right? This range tells you where m1 will lie, where the possible values of m1 can lie. It gives you directly the range in which m1 can lie, and it has a very specific meaning to it. It means some confidence, and that confidence in 95%. How do I say that? Yes, here's how. Let's do a normal, as always, a normal distribution, right? Let's say your t statistic, whatever your t statistic is, or what you'd call like your level of confidence. How much confidence do you want to have? Let's say I want to have 95% confidence. It's a very nice range. I want to have 95% confidence. That implies 5% of uncertainty, right? If you do a two-tailed test, because there are two sides to it, left and right, you divide it up, you block two ones. So this is 2.5%, 2.5%, and this is your 95%. You're claiming that your values of m1 for that very specific variable will lie in this range, right? And how do you find out that range? You do a function called qt model, right? So you do a function called qt in R. You'll find the appropriate one in Python as well, stats models, and sorry, SciPy, right? And you say that 0.025, which is 2.5%, and your df is, let's say, 429. It was in our example, right? So given your degrees of freedom, how many variables we have, which is n minus k minus 1, please remember that. And given this is the amount of confidence that you want to achieve, 95%. So this should be something along the lines of minus 1.97, right? What this value tells you is your t-test. Take the absolute value, right? So 1.97. From 1.97 you get a t value, right? And if you know your standard error, you automatically can get this range, right? From here, that means you can now say that I am 95% confidence that the slope of the variable or the coefficient of regression of that variable x1, which is m1, lie in this range, and you are 95% confident about it. That's the statement you can make. Now let's see how that looks like, right? So you're saying that 95% confidence interval for m1 is, let's say, minus 2.09, 7.17, some value, if you know that variable, right? So for m1, which is x1, technically you're doing it for x1. So for x1 is minus 0.209 to 7.17, right? So what you're saying is that this translates to this statement. This is how you're going to say it, right? So this is how you're going to say it. We are 95% confident that all the other variables, I mean, being equal. See, you're taking the null hypothesis state, right? You're saying that that specific variable is not zero. That's what you're saying over here. So all else being equal, which is equal to zero or something else, right? This model predicts that now you say some relation with y with respect to x1, right? You talk something about that this relationship scores 2.09 points confidence terms, right? Lower or 7.17 points higher than what would be opposite of x or complement of x. So it depends on what the value of x1 is, what is the meaning of x1 in your model is, right? So I've given you like a structure, right? So if there is a relationship between y and x1, so let's say price of the house with respect to the area square feet, right? So you said that the model predicts this relationship scores and is between 0.29 points to 7.17 points higher than the opposite of what x1 means, right? And this confidence level gives you the value of in which the range will lie, in which the influence will lie, with a 95% confidence interval. You can change it to 97. So if it's 97 over there, so you get 3%, divide 3% into 2, that's 1.5%. So 1.5 by 1.5, you do a qt function on it on 0.015 with a df of how many n minus k minus 1. You just calculate that, you will get a value that will be your t statistic, and from there you can automatically calculate what's the 97% confidence interval for that specific variable for that specific model, right? Then you can make statements like this. So this allows you to perform individual inferential statistic on each of the variables that you choose, or each of the predictor variables that you chose in your model, and see how important are they, and how much influence do they exert on the target variable y. This allows you to do that. So I want to quickly show you how it looks in Python, right? So if you remember the F statistic and T statistic that we're talking about, so this is in stats model API.
Can you zoom a bit, Debayan?
Yes, yes, yeah. Trying to, yeah. Can I think now it should be bigger, right? Okay. So stats model API.sm, right? So you're creating X and Y. You're adding in the intercept form, and then you're creating a model, right? You're getting a results. You're getting a parameters, which is your coefficient values. You're getting the t statistic results for each of them, right? That allows you to find out the confidence intervals for both of them, right? And then you can see the t statistic value for the specific intercept as well, right? And that allows you to also calculate the f statistic as well, right? Now how does it matter, how does it come down to this? In R we also get this. Can you see this statement? This is what important. This is the line that I explained, right? So this is your f statistic, this is the number of variables that you have k, this is your df, which is n, this is your p statistic for the model that you chose. So if this is your model, so your target variable is y is equal to dependent of m1 x1, right? And there is some data set here. So this is the significance of the model. You can see there is multiple, there is adjusted r square included over here. You can use that to compare between models if you want to. And yeah, that's it. It also gives you quick access to which variables are important and how do you work with that. So it all gives you the same information. And using that you can calculate the confidence intervals like I showed you over here. You can use that to calculate the confidence intervals for each of your variables and see how much influence do they impact on your target variable. So I want to. So this, at the end of the video, I want to just show you one way in which you can objectively create parsimonious models. You can create models that do not have any kind of collinearity on them, and they should be parsimonious by definition, right? And this is what you can do, right? So one is called backwards elimination. The other one is called forward selection. So this is how it works. Let's see our target model y, and this is your set of variables, right? So in backward elimination, right, is what you do is that you start with a variable, you start with a full model. You start with a full set of models, all the variables included, right? You find out an evaluation criteria for this. Depends on what you want. Do you want to use that F statistic p value thing that I talked to you about, right? F statistic combined with F statistic. Do you want to use that, or do you want to use R square? Might want to use adjusted R square, right? There are also a couple of other information like things like AIC, BIC, deviation information criterion, DIC, malloc CP. You have so many metrics, right? Choose the one that you like. Choose the one that you want to work with. Let's say p-value statistic or r square adjusted r square, right? You wanna choose any one of these evaluation variables, right? And based on these variables, you're gonna choose whether that model works for you or not, right? So you take the whole set, right? You take the evaluation metric. Let's say the evaluation for this model E1 is p-value. Let's say you take a p-value, a p-value is this one. Second time, you remove one variable, and that's it. You take the value of this one, E2. So if E2 decreases for E1, let's say your value is P value, right? So the less is better, or R square, adjusted R square, the more is better, right? So if you're using R square, then if E2 is more than E1, then Y is definitely the second model is definitely more parsimonious than the first model, and it produces the same result or better result, right? If it's p value, then the second model is more significantly statistically significant than the first model, right? And you can continue doing this until you're left with a null model, right? Y is equal to m1 x1 plus m2 x2 plus c. You have an evaluation criteria for this one, and then the fourth model will be m1 x1 plus c. You have a criterion for this one, and then in the fifth one you have nothing at all. That will be 5. So based on your metric, choose the one which is highest or lowest. If you're using p-value, choose the one with the lowest p-value. If you're using adjusted R square, choose the one with the maximum R square. If you're using AIC or BIC, you want to choose the one with the maximum AIC or BIC. If you're using malloc CP, you want to choose the one with the maximum malloc CP value, right? So this is a backwards elimination. You eliminate one variable, see whether the model improves or not. It's simpler or not. If it doesn't improve, then you delete another variable. You choose which one you want to remove so that you can decrease the value for that or increase the value for that criterion. And then you accordingly go till you cannot reduce any more variables. So you choose the one with the minimum or maximum value, right? Forward selection is literally the opposite of doing this, right? You start off with the empty model. You take a evaluation criteria. You take your evaluation value. You add one variable, you see the value, and so on and so forth. You get the idea, right? Over here, you're starting with the full model and you're going towards the null model, which is empty model effectively. In forward selection, you start with the null model and you go towards the full model, right? And you pick the one with the highest value or the minimum or the lowest value of the evaluation criterion that you choose. And you have so many to choose. If it's p value, look for the one with the smallest p value. If it's adjusted R square, choose the one with the maximum explainability, because R square means how much explainability in y, variability in y can be explained by the predictor variable. So that's good. AIC BIC, that's the Bayesian criterion, and Aikaki information criterion. So you want to increase the amount of information. That's what it means, that the model can predict using the set of combination of predictor variables. You want to increase that value. So for evaluation criterion for AIC, BIC, and DIC, you want to increase that. For malloc CP as well, you also increase that as well, right? So this is how you can create parsimonious models, given that you know what are the input variables are, you know what the target variables are, and you can qualitatively evaluate which one is your parsimonious model. This is a very simple way of doing so, and R as well as Python has automated ways of doing so. You give them all the variables that you need, you give them the target variable, they will automatically select the one with the best values of your specified evaluation criteria, right? So that's it for today, guys.
So, Debayan, that was all for the day, if I'm not wrong. And we
Mm-hmm.
learned a lot about how to use F-Statistic, how to use T-Statistics, how to use P-value. We learned about stepwise regression, like backward elimination and forward selection. That would help our audiences a lot. Do you have any more comments on this?
I would advise the audience watching this, learning from this, is to continually try to use the explanation that I gave, the way of interpretation that I gave in real life examples, and right, and be creative about how you use them. That's I would really advise the people.
Okay, so thank you, Devan, for your exciting and very interesting lecture on the inferential treatment using linear models. Guys, that was all for the day. Thank you for staying with us. If you want to support us, do give a comment, do like, do share the videos, and please subscribe to my channel. Guys, if you have any problem during the course of your journey, please do comment or follow us on our Discord server link down below, where I and Devan will always be there with you to help you guys out. Guys, it was your host Shubro. Along with me was
Debayan.
signing off. Bye bye.